Good afternoon, everyone. So this is my third report in abstract algebra. I am Arshel J. Colot and I am your discussant in this afternoon. So today we are going to tackle about the multiplicity of roots. So this is the continuation of the report of Ms. Libatog. So this time we are going to talk about the theorem 22.1.36 and the workout exercises. So first, we have theorem 22.1.36. Let f divides k be an algebraic field extension of characteristic b greater than 0, then k is purely inseparable where k is the separable closure of f of k. If f is equal to k, then the theorem is immediate. Suppose f is properly contains k of s. Let a element of f and a is not an element of k sub s. Let p of x is equal to k sub 0 plus k sub 1 x raised to p of e plus ellipsis p raised to p of e raised to n sub 0 be the minimal polynomial of f k where e is the exponent of the inseparability and n sub 0 is the reduced degree of p of x over k of s. Now, the theorem 22.1.15 k sub 0 plus k sub 1y plus ellipsis y raised to n raised to n sub 0 is the minimal polynomial of a raised to pe over ks, and this polynomial is separable over ks. Hence, a raised to p of e is separable over ks, thus ks, the quantity of a raised to pe divides ks is separable algebraic, and so ks, the quantity of a plus or a raised to pe divides k is separable algebraic. By the definition of ks, we have a raised to p of e element of ks. Therefore, a is purely inseparable over ks. Then the proof is already done. Next, exercises 22.1.39. Let k denote the field of the set of u and v, where u and v are algebraically independent over z. Let a be a root of a polynomial x raised to 2p plus bxp plus u over k. By the use of workout exercise 6 page 456, one can deduce that x raised to 2p plus bx raised to p and u is irreducible over k. Let f be the field of k of a. We ask the reader to verify the following properties of the field extension of f divides k. So k of s is equal to k raised to the quantity of a raised to p. So f is the function of k, I and pi, and f is the function of k is equal to 2. Also, extension f divides k has no elements which are purely inseparable over k, except those elements which are already in k. Thus, if J is intermediate field of f sub or divides k, consisting of all the elements, if f purely inseparable over k, then J is equal to k. Hence, f of J is not separable algebraic. 22.1.1 workout exercises. So, determine if the following polynomials are separable or inseparable. So, number 1, x squared plus 6x plus 9 over the set of the rational number. Then, the next is x raised to 4 plus x squared plus the set of 1 over g modulo 2. Solution. So x squared minus 6x plus 9 is equal to the quantity squared of x minus 3 over the set of a rational number. Now x minus 3 is irreducible over the set of all rational numbers. Since x minus 3 is separable over the set of rational numbers, x squared minus 6x plus 9 is separable over the set of all rational numbers. Number 2. X raised to 4 plus x squared plus the set of 1 is equal to the quantity squared of x squared plus x plus the set of 1 over g modulo 2. Now x squared plus x plus 1 has no roots in g modulo 2. Hence x squared plus x plus 1 is irreducible over g modulo 2. Now, the d sub x, the quantity of x squared plus x plus 1 plus 2x plus 1 plus 1 is not equal to 0. Thus, x squared plus x plus 1, and so x raised to 4 plus 2 plus 1 is separable over g modulo 2. Exercises 2. Prove the following polynomials are irreducible over g modulo 3t, where t is transcendental over g modulo 3. Find the exponent of inseparability and the degree of separability of the polynomials over g3t. Number 1. The function of p of x is equal to x raised to 36 plus tx raised to 18 plus t. Number 2. Q of x is equal to x raised to 24 plus tx raised to 18 plus t. R of x is equal to x raised to 20 plus tx raised to 18 plus t. Then S of x is equal to x raised to 9 plus t. Solution. Since t of t, then t divided 0 of t is not divided by 1, t squared is not divided by t. The polynomials of p of x, q of x, r of x, s of x are irreducible over g modulo 3t. So the first is p of x is equal to x raised to 4 times 3 squared plus tx raised to 2 times 3 squared plus t, and so the exponent of inseparability e is equal to 2 and the degree of separability n sub 0 is equal to 4. Number 2, q of x is equal to x raised to 8 times 9 plus t of x raised to 6 times 3 plus t, and so the exponent of inseparability e is equal to 1 and the degree of separability n sub 0 is equal to 8. Next is, since 3 is not divided by 20, e is equal to 0 and n sub 0 is equal to 20. Then the last, here is e is equal to 2 and n sub 0 is equal to 1. Example, exercises 4. Let k is equal to p, the sets of x, y, z, and f is equal to k, the quantity of 2 raised to p negative 1, z, p raised to 2, then z raised to p negative 1, plus y raised to p negative 1, where p is the perfect field of characteristic p not equal to 0, and x, y, z are algebraically independent intermediates over p. Prove that k raised to p negative 1. So solution, so clearly f is a properly contains k raised to p negative 1 of f contains k, the quantity of z raised to p negative 1. Now, the function of f on k is equal to p raised to 3. Suppose that kp negative 1, f contains k, the quantity of g raised to p negative 1, and then f is equal to k raised to p negative 1 of f multiplied by z raised to p negative 2, since it's not the element of k raised to p negative 1, f and Okay, so since G remains linearly independent over K, therefore G raised to P negative 1 and Y of P raised to P negative 1 is element of F. Thus, the function of F of K is equal to P raised to 4. So that would be all this afternoon, and thank you.